For more than a century, scientists have been fascinated by the concept of black holes. This idea began gaining significant attention in 1916. These celestial anomalies remain some of the most fascinating and mysterious phenomena we've discovered, residing at the intersection of immense gravitational forces and an elusive nature that defies our comprehension. A black hole, which could potentially have a mass between 2 to 4 million times that of our Sun, persists as an enigmatic feature in the cosmos. Even after decades of focused research, our knowledge has evolved from nearly nothing to gradually assembling more details, with fresh breakthroughs continuing to emerge. A recent discovery by Michio Kaku has presented shocking revelations about the interiors of black holes, which could potentially challenge established beliefs and offer new viewpoints on these cosmic objects. This fresh data opens up pathways for deeper exploration into previously overlooked aspects. Join us as we delve further into the compelling world of black holes and uncover what might be hidden in the vast universe. Before diving into Kaku's latest findings, it's important to revisit what we already know about black holes. Although most people have a basic understanding of black holes, key elements remain unclear. In 1916, Albert Einstein's groundbreaking general theory of relativity predicted that black holes existed. At that time, the idea was purely theoretical. It wasn't until around 50 years later that concrete evidence confirmed black holes as real entities in space. This confirmation came in the 1960s during studies of the celestial object Cygnus X1, a bright source of X-rays. Observations showed these X-rays were not just random but were being drawn into a dense, invisible mass. This mass, later identified as a black hole, completely changed our view of the cosmos. The discovery was groundbreaking, proving black holes weren't merely hypothetical but actual, elusive objects that required further study. Following this revelation, scientists from all over the world launched a collaborative effort to learn more about black holes. This led to the realization that the Milky Way alone may contain around 100 million black holes. However, due to the immense difficulty in detecting them, this estimate remains speculative. While pinpointing black holes is extremely challenging, scientists suspect that millions of these massive bodies are concealed within our galaxy, making it even more crucial to understand their properties. The fundamental idea of gravity. Black holes exert gravitational forces so extreme that anything that enters their domain is crushed into a singularity, a point where the very laws of physics break down. In simpler terms, black holes act like gigantic vacuum cleaners, drawing everything in. One of the most terrifying aspects of studying black holes is the thought of someone falling into one. As they approach the singularity, they would be stretched apart by the immense gravitational forces, ultimately being torn to pieces before complete destruction occurs. It's best to stay a safe distance away. Despite black holes being scattered throughout the universe, the nearest one is nearly 500 light-years away. While that distance is vast, the closeness is still concerning. A historic milestone. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This was made possible after countless nights spent taking photos and aligning them into a unified image. As more data was collected, researchers discovered that black holes consist of 3 distinct layers, contrary to the common belief that black holes are simply endless voids. These 3 layers are fundamental to understanding their structure. 1. The event horizon marks the point beyond which nothing can escape the black hole. Once something crosses this boundary, it is inevitably drawn in. 2. The photon sphere, the region where light itself is trapped, unable to break free due to the black hole's immense gravitational pull. 3. The singularity, a point where all matter is compressed to an infinitesimally small size, where the very fabric of reality collapses, and physics as we know it ceases to function. Each black hole is unique in its characteristics. While they generally follow this 3-layer structure, their behavior can vary greatly. This makes them particularly challenging to study, as conventional scientific techniques don't apply. Researchers can only study them indirectly by observing the radiation emitted or by analyzing the gas and dust surrounding them. Directly sending a probe into a black hole would be futile, as anything that crosses the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. Given this, spending billions of dollars on probes that will provide no useful data is not a viable option. Thus, scientists must study black holes in 2 dimensions, despite their 3-dimensional nature. The complexity of black hole research. Adding to the difficulty of black hole research is the fact that no 2 black holes are exactly alike. When studying them, we must take into account the breakdown of known physics, as black holes present a situation where both quantum mechanics and general relativity must be considered. Theories suggest black holes are born when massive stars collapse under their own gravity. As a star consumes its fuel, it can no longer produce enough energy to counterbalance the gravitational forces pulling inward, leading to the collapse into a singularity. To further study black holes, NASA scientists turned their focus to the center of the M87 galaxy, where they observed a powerful whirlpool of hydrogen gas spinning at an astonishing 1.2 million miles per hour. This gas should have scattered due to centrifugal forces but instead remained intact, indicating the presence of a massive object at the center, most likely a black hole. It is believed that this object could have a mass up to 3 billion times that of our Sun. Roy P.'s theory. In 1963, New Zealand mathematician Roy P. proposed a significant theory using Einstein's equations to describe rotating black holes. He suggested that instead of collapsing into a single point, as previously thought, a rotating black hole forms a thin, ring-like structure known as the ergosphere. This rotating disk of matter is crucial for understanding the breakdown of physical laws near black holes. Roy's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole capable of providing a shortcut through spacetime, connecting distant regions of the universe or even alternative universes. The concept of wormholes. To understand the concept of a wormhole, we must first grasp Einstein's notion of spacetime. According to Einstein's theory, spacetime is a four-dimensional fabric that is warped by objects with mass, creating gravitational fields that influence the movement of other objects. Imagine spacetime as a piece of paper. If you fold it, you create a shortcut between 2 points. This fold represents a wormhole, a potential passage through spacetime that could link distant locations instantaneously. While wormholes are a theoretical idea and no concrete evidence exists for them, they are a natural consequence of general relativity. However, wormholes are unstable by nature, meaning they would collapse rapidly if formed. Superstring theory, a path to the theory of everything. Superstring theory suggests that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. These strings exist in multiple dimensions, far beyond the 3 spatial dimensions and 1 time dimension we experience daily. The vibrations of these strings determine the properties of different particles, including mass, charge, and spin. One of the most intriguing aspects of superstring theory is its ability to unify quantum mechanics and general relativity, which traditionally have been at odds. While Einstein's theory of relativity explains gravity on large cosmic scales, quantum mechanics governs the behavior of particles at subatomic levels. Black holes, with their extreme density and gravitational pull, sit at the crossroads of these two realms, making them the perfect testing ground for a theory of everything. Black hole information paradox. One of the biggest mysteries surrounding black holes is the information paradox. According to classical physics, any object that falls into a black hole is lost forever. However, quantum mechanics suggests that information can never be truly destroyed. This contradiction has puzzled physicists for decades. Stephen Hawking introduced the concept of Hawking radiation, a process in which black holes emit tiny amounts of radiation due to quantum effects near the event horizon. Over time, this causes the black hole to lose mass and eventually evaporate. If this is true, what happens to the information that fell into the black hole? Does it vanish completely, violating the laws of quantum mechanics? Or is it somehow encoded in the Hawking radiation? Recent research suggests that black holes might not destroy information after all. Some theories propose that the event horizon acts like a holographic surface, storing information in a way that could theoretically be recovered. Others believe that information may escape through quantum entanglement or wormholes, linking distant regions of spacetime. Could black holes be gateways to other universes? One of the most speculative yet fascinating ideas is the possibility that black holes could serve as portals to other universes. Some physicists suggest that when matter falls into a black hole, instead of being crushed into a singularity, it could be transported through a wormhole to another part of the cosmos, or even an entirely different universe. This idea is based on the concept of white holes, the theoretical opposites of black holes. While black holes pull in everything, white holes theoretically expel matter and energy. Some theories suggest that every black hole could be connected to a white hole, creating a tunnel between two universes. While this remains purely speculative, advances in quantum gravity and string theory may one day provide evidence for these exotic phenomena. The future of black hole research. As our technology advances, so does our ability to study black holes. Future telescopes, such as the James Webb Space Telescope and the Event Horizon Telescope, aim to provide clearer images and more data on black hole behavior. Additionally, upcoming projects like the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from merging black holes, offering new insights into their structure and origins. Despite the challenges, black hole research continues to push the boundaries of human knowledge. What was once considered science fiction is now at the forefront of cutting-edge physics. As we continue to explore the cosmos, black holes may hold the key to unlocking some of the deepest mysteries of the universe. Theory, which posits that subatomic particles are actually tiny vibrating strings. This theory proposes that these strings form the very fabric of the universe, explaining not only gravity but also the phenomena surrounding black holes and wormholes. However, superstring theory also requires the existence of extra dimensions of spacetime, which are so minuscule that they are undetectable with current technology. Despite the difficulties in testing superstring theory, its mathematical elegance and coherence make it one of the most compelling ideas in theoretical physics. At the same time, scientists are exploring other approaches that could lead to breakthroughs in understanding black holes. For example, quantum gravity is another field of research aiming to merge quantum mechanics, which governs subatomic behavior, with general relativity, which explains large-scale phenomena like planets and black holes. By merging these two theories, scientists hope to gain clearer insights into how gravity operates on a quantum level and better understand black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is especially important when studying black holes, as the extreme conditions near their event horizon, where gravity is incredibly strong, demand a theory that can account for both quantum and relativistic effects. The interior of a black hole, where the singularity exists, is one of the most puzzling environments in the universe. The singularity represents a point where space and time are so warped that traditional physics no longer applies. Understanding this requires a theory capable of reconciling quantum mechanics and general relativity, which has led to the development of ideas like loop quantum gravity and other quantum gravity models. As we continue to probe black holes, one thing is clear: the more we learn, the more we realize how much is still unknown. Black holes are not only destructive forces but also places of immense complexity and potential. Whether they are portals to other dimensions, as some theorists propose, or hold the key to understanding space and time, black holes remain a critical area of study. As our tools and theories evolve, so too will our understanding of these enigmatic objects. Looking ahead, the next challenge will be refining our methods for observing and studying black holes. One of the most promising recent advancements has been the development of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the movement of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can learn about the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into black hole mergers, and future experiments are likely to offer even more revelations. In addition to gravitational wave research, the use of advanced telescopes and imaging techniques is another exciting area of study. The Event Horizon Telescope, EHT, which captured the first image of a black hole in the M87 galaxy, shows how innovative technology can provide new insights into black holes. By combining data from multiple radio telescopes worldwide, the EHT was able to capture an image of the black hole shadow, giving us a glimpse into one of the universe's most mysterious phenomena. As technology continues to improve, we can expect to observe black holes with even greater precision, revealing more about their structure, behavior, and role in the cosmos. The study of black holes is not just about understanding these strange objects in isolation, it's also about exploring the fundamental principles of the universe. By studying black holes, we're learning more about the laws that govern spacetime, gravity, and the very nature of reality. In conclusion, the study of black holes represents one of the most exciting and challenging areas of modern physics. With every new discovery, we inch closer to unraveling the mysteries of these cosmic giants. Whether through gravitational wave analysis, imaging technology, or new theoretical frameworks, black holes continue to capture the imaginations of scientists and the public alike. As we delve deeper into these mysterious entities, we may be on the verge of unlocking some of the greatest secrets of the universe, perhaps even answering questions that have eluded humanity for centuries. The ongoing research into black holes is leading us to a deeper understanding of not only these mysterious objects but also the broader workings of the cosmos. The more we learn, the more evident it becomes that black holes are far more than just cosmic phenomena to be studied in isolation. They represent crucial pieces of the puzzle that could unlock answers to questions that have baffled humanity for centuries. Our exploration into these enigmatic entities may very well hold the key to some of the universe's most profound mysteries. The next big frontier in this field of study involves improving our observational techniques and refining our theoretical models. Recent advancements in gravitational wave astronomy have already made significant strides. By detecting and analyzing gravitational waves, ripples in spacetime caused by the acceleration of massive objects, such as black hole mergers, we are now able to observe the behavior of black holes in ways that were previously unimaginable. The detection of these waves has already provided groundbreaking information, such as insights into the dynamics of black hole collisions, and researchers are optimistic that further studies will lead to even more exciting revelations. Additionally, the development of cutting-edge telescopes and imaging techniques is opening new doors in black hole research. The Event Horizon Telescope, EHT, made history when it captured the first-ever image of a black hole located in the M87 galaxy. This achievement, made possible through the collaborative efforts of radio telescopes across the globe, allowed scientists to capture the shadow of a black hole, offering a glimpse into one of the most mysterious and elusive phenomena in the universe. As technology continues to evolve, we can expect even higher resolution images of black holes, providing deeper insights into their structures, behaviors, and their essential role in the larger cosmic picture. In fact, the study of black holes isn't just about understanding these objects in isolation. They serve as critical laboratories for testing the fundamental laws of physics, especially the intersection of spacetime, gravity, and quantum mechanics. By studying black holes, we are not only expanding our knowledge of these unique objects but also improving our understanding of the universe as a whole. These investigations have the potential to lead to breakthrough discoveries that could fundamentally reshape our understanding of the laws governing the cosmos. As our understanding of black holes deepens, new questions continue to emerge. One of the most intriguing mysteries is the nature of the information paradox, a problem that arises from the apparent contradiction between quantum mechanics and general relativity. According to classical physics, any matter that falls into a black hole is lost forever. However, quantum mechanics suggests that information cannot be destroyed. This paradox has led physicists to explore potential solutions, including the idea that information may be preserved in a holographic form on the event horizon or that it could be encoded in subtle quantum correlations known as Hawking radiation. Recent advancements in theoretical physics have proposed that black holes may not be as final as once thought. Some models suggest that black holes could slowly evaporate over time, releasing information in a way that remains consistent with the principles of quantum mechanics. If these theories hold true, they could revolutionize our understanding of spacetime and the fundamental nature of reality. Another exciting avenue of research involves the potential link between black holes and the early universe. Some scientists speculate that the conditions within a black hole could mirror those of the Big Bang, offering a unique window into the origins of the cosmos. There is even the possibility that black holes could serve as gateways to other regions of the universe, or even to entirely different universes, through hypothetical structures known as wormholes. While these ideas remain speculative, they highlight the profound implications that black hole research could have for cosmology and fundamental physics. Looking ahead, future missions and technological advancements will play a crucial role in furthering our understanding of black holes. Space-based observatories, such as the proposed Laser Interferometer Space Antenna, LISA, are expected to revolutionize gravitational wave astronomy by detecting lower frequency waves than current ground-based detectors can observe. This will allow scientists to study a broader range of cosmic events, including the mergers of supermassive black holes in distant galaxies. Additionally, next-generation telescopes, such as the James Webb Space Telescope and upcoming radio telescope arrays, will provide even more detailed observations of black holes and their surrounding environments. These instruments will enable researchers to study the accretion disks, jets, and magnetic fields around black holes with unprecedented clarity, shedding light on the complex processes that govern their behavior. As our exploration of black holes continues, one thing remains certain: they are far more than just cosmic enigmas. They serve as natural laboratories for testing the limits of physics, offering insights into the nature of space, time, and matter itself. With each new discovery, we edge closer to unlocking the secrets of these extraordinary objects, secrets that may ultimately reshape our understanding of the universe and our place within it. The journey to comprehend black holes is still in its infancy, but the progress made so far is nothing short of remarkable. As scientists push the boundaries of knowledge, we can only imagine what astonishing revelations lie ahead. Whether through breakthroughs in quantum gravity, new observational techniques, or unexpected discoveries, black holes will undoubtedly continue to challenge our perceptions and inspire future generations of researchers to seek answers to the universe's deepest questions.